The orbital eccentricity of an astronomical object is a parameter that determines the amount by which its orbit around another body deviates from a perfect circle. A value of 0 is a circular orbit. Values between 0 and 1 form an elliptical orbit. 1 is a parabolic escape orbit, and greater than 1 is a hyperbola. The term derives its name from the parameters of conic sections, as every Kepler orbit is a conic section. It is normally used for the isolated two-body problem, but extensions exist for objects following a rosette orbit through the galaxy. Etymology. From medieval Latin eccentricus, derived from Greek kappa kappa epsilon nu tau omicron sigma ekantros, out of the center, from kappa ek, out of, plus kappa epsilon nu tau omicron nu kenton, center. Eccentric first appeared in English in 1551, with the definition of circle in which the Earth, Sun, etc., deviates from its center. 5 years later, in 1556, an adjective form of the word was added. Examples: the eccentricity of the Earth's orbit is currently about 0.0167. The Earth's orbit is nearly circular, over hundreds of thousands of years. The eccentricity of the Earth's orbit varies from nearly 0.0034 to almost 0.058 as a result of gravitational attractions among the planets. Mercury has the greatest orbital eccentricity of any planet in the solar system. Before its demotion from planet status in 2006, Pluto was considered to be the planet with the most eccentric orbit. The Moon's value is 0.0549. Sedna, the most distant known trans-Neptunian object in the Solar System, has an extremely high eccentricity of 6,999,854,910,000,000 spadesuit 0.854991 due to its estimated aphelion of 937 astronomical units and perihelion of about 76 astronomical units. For the values for all planets and other celestial bodies in one table, see List of gravitationally rounded objects of the Solar System. Most of the Solar System's asteroids have orbital eccentricities between 0 and 0.35 with an average value of 0.17. The comparatively high eccentricities are probably due to the influence of Jupiter into past collisions. Comets have very different values of eccentricity. Periodic comets have eccentricities mostly between 0.2 and 0.7, but some of them have highly eccentric elliptical orbits with eccentricities just below 1. For example, Halley's comet has a value of 0.967. Non-periodic comets follow near parabolic orbits and thus have eccentricities even closer to 1. Examples include Comet Hale-Bopp with a value of 0.995 and Comet C 2006 P1 with a value of 7,100,100,900,000,000 spadesuit 1.00019. As Hale-Bopp's value is less than 1, its orbit is elliptical and it will in fact return. Comet McNaught has a hyperbolic orbit while within the influence of the planets, but is still bound to the Sun with an orbital period of about 105 years. As of a 2010 epoch, Comet C 1980 E1 has the largest eccentricity of any known hyperbolic comet with an eccentricity of 1.057, and will leave the Solar System indefinitely. Neptune's largest moon Triton has an eccentricity of 6,995,160,000,000,000 spadesuit 1.6 times 10⁻⁵. The smallest eccentricity of any known body in the Solar System, its orbit is as close to a perfect circle as can be currently measured. Mean eccentricity The mean eccentricity of an object is the average eccentricity as a result of perturbations over a given time period. Neptune currently has an instant eccentricity of 0.0113, but from 1800 to 2050 has a mean eccentricity of 6,997,859,000,000 spadesuit 0.00859. Climatic effect. Orbital mechanics require that the duration of the seasons be proportional to the area of the Earth's orbit swept between the solstices and equinoxes. So when the orbital eccentricity is extreme, the seasons that occur on the far side of the orbit can be substantially longer in duration. Today, northern hemisphere fall and winter occur at closest approach, when the Earth is moving at its maximum velocity, while the opposite occurs in the southern hemisphere. As a result, in the northern hemisphere, fall and winter are slightly shorter than spring and summer, but in global terms this is balanced with them being longer below the equator. In 2006, the northern hemisphere summer was 4.66 days longer than winter and spring was 2.9 days longer than fall. Apsidal precession slowly changes the place in the Earth's orbit where the solstices and equinoxes occur. Over the next 10,000 years, northern hemisphere winters will become gradually longer and summers will become shorter. Any cooling effect in one hemisphere is balanced by warming in the other, and any overall change will, however, be counteracted by the fact that the eccentricity of Earth's orbit will be almost halved, reducing the mean orbital radius and raising temperatures in both hemispheres closer to the mid-interglacial peak.